Okay, now I'll show you how to measure depth from a single camera using ArUco markers in OpenCV. Let's see this example. You see there's one ArUco marker here, and you see the values in top left. These are meters, so x, y, depth, and distance. So if you want to follow this video, first you need to calibrate your camera, and I have a separate video and article about this. It took about 5 minutes, and you only need camera, chessboard, and ruler. So it's not that hard, using OpenCV within like 10 minutes. Everything will be done for you if you follow this article. Of course, you don't have to stick with this article. You can use any other resources for that. But in the end, you will have to have like this kind of parameters. So I assume that you followed something and you got these parameters, camera matrix and distortion coefficients. So these are basically intrinsic parameters, and these are distortion coefficients. So I will share a link to this article and this one in comment section. You can follow this. And before starting the coding, I will quickly explain what are the ArUco markers. So these are basically binary images. You see the examples here, and there's not one ArUco marker. There are different dictionaries. And let's see this one, for example. This 50 means that there's 50 unique combinations in this specific dictionary, and 4 times 4 means that there's 16 total bits. Yeah, same with this one, 250 unique combination and 36 bits. Yeah, for example, you see this image here. Let's see the second row, like bit number 1, 2, 3, 4, 5, 6. So this means that this specific marker is belong to this dictionary. Yeah, you can use any dictionary, any marker, but you just have to stick with what you choose, because later in the code you have to use same dictionary. And yeah, and before starting, let's say that you want to test, you choose an ArUco marker from this website or any other website. You can click this link. Let's say you choose this with this dictionary, and you printed this onto some paper or any other thing. You have to measure one side of this specific marker. Yeah, for example, I'm using my mobile phone, and you see here it's around 26 or 27 millimeter. You need to measure this length, and you have to save it. We will use later this inside the code. You see here marker length. So before starting, you need to calibrate your camera, and you need to generate one ArUco marker, and you need to measure the one side of this specific square. And after that, you can copy this code block into your local, and you only need to install OpenCV and NumPy. You can open a terminal and pip install OpenCV Python and NumPy like this. So after that, you can directly use this code. And first, I will show you, how this works, and I will explain the code later. Let me run this ArUco. Yeah, you see here. By the way, these values are specific to my camera. You cannot use these values because results will be not accurate. So for every different camera, these values will be changed. And let me run this. Yes, you see the ArUco marker on my mobile phone, and you see the values. Yeah, for example, as I move my camera close to my webcam, that value is approaching to 0. And as I move like this, you see, because of the lighting, it cannot detect all the time, but in normal daylight, it detects perfectly. Yeah, you see, for example, depth value is increasing. And let's say I'm going like horizontally, and you see the x value. Y value is like same, but x value is changing. Yeah, you can test like this. And now let me explain the code for you. First, we are importing three libraries, and we are loading calibration data from this YAML file. And after that, you need these three things I just explained to you: intrinsic parameters, this camera matrix, distortion coefficients, and marker length. And after that, you see here, this is the dictionary. Yeah, I generated my ArUco marker from this specific dictionary from that website, so I'm sticking with the same dictionary. This is important. And after that, here we created detector instance. You can check source code if you're interested. And you don't have to stick with webcam, you can use normal videos as well, but I will stick with webcam. So I'm reading frames one by one. And after that, using detect marker method, we are detecting markers. So it returns like corners IDs. You see the example output of corners here. These are like 2D image coordinates, nothing special. These are not real length values, just pixel values. Like top left is 0, 0. So these are the 4 corners. Actually, I think we can print these for you to understand better. Print corners. So I will print these corner coordinates, and let me run like this, Python. Okay, yeah, you see these are normal image coordinates, like pixel coordinates, nothing special. So we will use these later. And after this, after detecting markers, if any marker is detected, so if ID is not none and it is greater than 0, we are moving forward. Yeah, using draw detected markers, you can draw these, like you can draw rectangle around specific marker. Yeah, it's not that necessary, but it's great to visualize that. So this part is important, and it might be a little complex, not that complex, but so we are here, we basically define the 3D coordinates of the marker corners in the markers coordinate system. This part is important. Again, I'm saying markers coordinate system. So I will explain this inside Paint. It will be better. Let's say this is our ArUco marker, and here we have coordinate system. Let's call here X, and here Y. So here is the origin. Remember, this is markers coordinate system, not any other thing. And we want to define 3D coordinates of the four corner. So here, here, and here. Yeah, for the first one, we need to go here. So this will be like minus marker length divided by 2 for X here. And for Y, marker length divided by 2 in positive. So here. And for example, for the second corner, we need to go right. So this will be positive, marker length divided by 2 here. And for up, we need to go marker length divided by 2, just like in first corner. So process is same for other two corners, this 3 and 4. And for Z values, these are all 0 because they are in same plane. We didn't change any depth, any Z value, so these are all 0. So we will use these 3D coordinates and 2D coordinates in solvepmp function. So it basically estimates the pose of a 3D object given its 3D points, which are this block, and corresponding 2D image points, this part. And of course, using camera matrix and distortion coefficient values inside this YAML file. So using these 4 things, it will estimate the pose of specific marker. The solvepmp function, by the way, you can check documentation for that. Let me show you. Yes, the solvepmp and related functions estimate the object pose given a set of object points. Yes, their corresponding image projections and intrinsic matrix and distortion coefficients. Exactly, that's what we did. Yeah, if you're interested in math, you can read here. Okay, let me continue. So this solvepmp returns, rotation vector and translation vector. So this translation vector basically contains real world values, like in Matter. So if this return anything, here we are first drawing frame axis. It's not that necessary, but it's great to visualize this, just like this. Where was that? Yes, this one. So after that, using this translation vector, we are extracting the distance values. Yeah, this is normal vector, by the way, that contains, the distance values. I will print that. Let me run this. So you'll see that in terminal. Okay. Yeah, you see. And when you flatten this translation vector, it will be like values one by one, nothing special, X, Y, and Z. When you flatten this, you can reach values one by one. And using this translation vector, you can calculate the magnitude, and this will be distance, and you can print all of these values. Yeah, I think that's it. And this part is all about, in top left, remember, let me show you Python. Yeah, if you see top left right now, you'll see X, Y, depth, and distance values. Yes. Yeah, you see, like, yeah, as I said you before, you can use different markers. You see how values are changing. I'm going right, for example. And let me check if I missed anything. Yeah, as I said you before, because of the lighting conditions, detections are not that perfect all the time in nights, but if you experiment it with in daylight, it will be better than this. And I think that's it for this video. Thanks for watching. See you soon.